Next, we discuss the asynchronous BCD counter. Okay, asynchronous BCD counter can also be called as asynchronous decade counter. You know the meaning of the word decade. It means 10. I mean, for a decade, we'll say that is a period of 10 years. Okay. Similarly, here what we do is we go for BCD design, that is asynchronous BCD design. That's also called the asynchronous decade counter design. Okay. Okay, we will go directly into the basic the basic points that we need to discuss, and after that we will go directly into the design phase. Okay, so the modulus of a counter is the number of unique states through which the counter will sequence. The maximum possible number of states, that is maximum modulus of a counter, is 2 raised to n, where n is the number of flip-flops in the counter. What we need to understand from all these cases is that what is the significance of 2 raised to n, where n is the number of flip-flops, means in the case of BCD counter, in BCD from 0 to 9, that is 0000 to 1001 is considered as the what we call the valid states, and the rest of the values are considered as the invalid states, right? So what we need to understand is 2 raised to n, that what is the significance of 2 raised to n means here we need, that is the last statement I have written, is the decade counter requires 4 flip-flops. Okay, so how can we compute, what is the, in questions there may be in some cases we may receive a question, we may get a question saying that design a 3-bit, design a 4-bit, design a 2-bit, likewise. But in some cases we don't receive such questions. I mean, we don't receive such specific numbers. Okay, 2, 3, 4, likewise. So what we need to understand is we need to from the design point of view, we need to think and we need to come into a conclusion that how many flip-flops is required in this particular case. Okay, BCD is such a kind. Okay, what we need to understand is we know that 0 to 15 means there are 16 states, and we have 2 raised to 4 is 16. Okay, and the rest of the values, that is 10, what we call 0 to 9 is valid, 10 to 15 is invalid. Okay, in the case of BCD. Okay, but 0 to 15 means 16 states are there, that is 2 raised to 4 is 16. So always go for, if someone asks you how can we design a what we call a BCD counter, what we need to do is we need to understand that there are even though there are 6 invalid states, we need to understand there is 0 to 9 is there. 0 to 9 means there are 10 cases, right? 10 cases are there. So the rest is we need to go for how we need to calculate, that is 2 raised to n. 2 raised to 3 means that is to 8. Okay, 8. So 2 raised to 4 means it's 16. So always go for higher cases, that is 2 raised to 4. Okay, don't go for lower cases. Okay, and such sequences in which, or such designs in which, or such counters in which we have found how many flip-flops we need, but in some cases, in this BCD case, it's clear that 6 cases are invalid, right? So in such cases, all these cases, that is 0 to 15 is not used. So in such cases we cut short the number of states. Such a condition is called truncated sequence. Okay, that is our next point. Counters can be designed to have a number of states. Counters can be designed to have a number of states in the sequence that is less than the maximum of 2 raised to n. This type of sequence is called truncated sequence. One common modulus for counters with truncated sequence is 10 mod 10. Okay, mod 10. Mod 10. Okay, counters with 10 states in their sequence are called decade counters. A decade counter with a count sequence of 0 through 9. Okay, 0 through 9 means 10 states. Okay, is a BCD counter because its 10 states produces the BCD code, and the BCD counter requires 4 flip-flops, the reason I have told you just now. Okay, please go through. This is the design of BCD counter, asynchronous. Okay. Without this particular case, it's similar to a normal counter, a normal binary counter. Here we can say that a normal 4-bit binary counter. Okay. And what happens next is, actually in the case of BCD counters, the numbers 0000 to 1001, that is 0 to 9, that's those 10 states will be counted. Okay. And we are, in the case of design, we are not going to show whether the rest of the cases are valid or invalid. Actually, how a binary counter works is, in the case, in the previous case, a normal binary counter works is, we have 0, 1, 2, 3, and after that it repeats, right? Okay. In the case of 2-bit, the case of 4-bit, and the case of 3-bit, after 7, from 8 onwards, it starts repeating from the initial case. So, in the case of BCD counter, how the output should be, that means, we have 0000, that is 0, 0 to 9. And after that, 10 should not be there. We need to go back to, from 0 to 9, then go back to 0, again 9, after 9 again, not 10, go to 0, again 9, likewise. Okay, that is 0 to 9, those 10 states should be there. So, if a normal circuit with 4 flip-flops is drawn, what happens is, it goes on printing the numbers from 0 to 15, but we are designing a BCD counter. So, we need to perform a particular operation, and that's called decoding. Okay, here the name of this particular decoding is called partial decoding. Partial decoding. Okay, what is the significance of partial decoding? Here we have taken the output from Q3 and Q1. Okay, as I had told before, number 0000 to 1001 is valid, and after that we have 1010. Okay, same as we discussed earlier. When we draw the figure, we draw the flip-flop from this manner to that way, from left to right, but actually how it is read means in the opposite direction. What I told in the previous case, that is, in the previous normal binary computation of binary counter design, what we did is, we have Q0, we have Q1, Q2, Q3, but we read the output as Q0, Q1, Q2 and Q3. Remember that. Okay. Same is the case we read here also. That is, we have 0, 0, 0, 0 in the first case. Okay. Next we have change happen here. So 0, 0, 0, 1. Then 0, 0, 1, 0. Likewise, this operation or this type of this happens till we have 1, 0, 0, 1. Okay, 1, 0, 0, 1 means it's 9. Got it? After 1, 0, 0, 1, what will be the next number? It will be 1, 0, 1, 0. Okay, 1, 0, 1, 0. 1, 0, 1, 0. Clear? What is the significance of 1, 0, 1, 0? It's 10. It means that after 0 to 9 states, the invalid condition also came into the action, right? So what we need to do? We need to perform a partial decoding. Partial decoding means we don't, this is the only case. That is, these two are the only cases. Just I think you can follow me. That is, these are the only cases. That is, 1, 0, 1, 0 is the only number. Other numbers, that is 0, 0, 0, 0, to 1001 does not contain one values, both those values should contain, does not contain one values in Q3 and Q1 position. Q3 and Q1 position. No numbers from 0000 to 1001 contain one values, this one value in Q3 and Q1 position. Okay. Once we go to 1001, that is 9, obviously we will get the next number as 1010. So what we do is, we take the output value 1, we take it here, we take the output from this case, from Q1, this is 1 and 1. This is NAND gate. 1.1 is 1. In the case of NAND, the output will be 0. Clear? 1.1, the whole bar. Okay. So this 0 will be fed to all these cases. Hope you understood. Okay. Taking Q3 value, taking Q1 value, performing NAND operation, and taking the output, that is 0, should be fed to all these cases. What will be the net result? The output will be 0000 to 1001. 9. That's the value, 9, right? The 10th value, that is obviously the operation is taking place. Okay. Obviously, the next number will be definitely what? 1010, that is 10. But after the 9th operation, or after getting, we perform the partial decoding. There, we need to take these two values and perform this operation, and we feed this clear or the 0 value to all these cases. In effect, what we achieve is, we receive 0000 to 1001, that is 9, and after that we have 1010, but what happens is, we had such a decoding, partial decoding. Okay, so the result will be, next value will be 0000 again. Got it? This is how we perform partial decoding. Okay, and some people might be thinking, we converted 1010 to 0000 only after the 9th stage. We went to the 10th stage, and from there we took this particular value, right? Some people might be thinking like that. But actually what happens is that, as I told once, these all takes place within nanoseconds, or what we call values less than seconds in the case of proper functioning. Okay, so from our naked eye receives only 0000 to 1001, that is 9, and the next, for fractions of seconds or nanoseconds, there is 10. Okay, that is 1010. But within that nanoseconds range, what happens is, this particular value, that is partial decoding, takes place, and 0000 is fed back to the flip flops. So what we see is 0000 to 1001. After that, no 1010. After 1001, we go to 0000. Okay, and when we go for the waveforms, we observe a glitch. 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 What do you mean by glitch? Just what I told right now. That is, for nanoseconds range or particular period of time, we actually went to the 10th stage, that is the case 1 of invariant condition. Okay, after 0000 to 1001, that is 9, we went to the 10th value, but just for nanoseconds range. So when we draw the waveform, we will see that Q1 had a glitch, that is a small, what we call a small time difference. Okay, so when we go for the waveform, please draw that also. I will give the waveform also. Okay. Yes. as this is a 4-bit case, we have 4 flip-flops and we have Q0, Q1, Q2, Q3, and the problem arises and or you know actually if there was no issues, Q1 should have been, you know, it should go to a higher case. Okay, that's the pattern. Okay, but due to glitch, that glitch means that due to that time difference in the case in what we call nanoseconds range, that's called glitch. Okay, it actually reached the 10 stage, but what we call the value 10, but it is not shown for just fractions of seconds or nanoseconds. Okay, and this is the other case, that Q3. We took the output from Q3 and Q1, right? So this is Q3. Actually, this should follow this path, but what happened is, due to glitch, that is also another case. Okay, and this is what is called glitch. Okay, and this is very easy. This particular case, as I have already told you how to design the binary values. Okay.